Okay, in this video I'm going to talk about arithmetic logarithmic derivative. So recall that the arithmetic derivative, not logarithmic, but just the full arithmetic derivative is defined. So it is a function d from natural numbers to natural numbers, and it is defined by two properties. So first, that it is equal to 1 for all prime numbers. So for all prime number p, we have d of p is equal to 1. And the second is the product rule, similar to the regular derivative for derivative of functions in mathematical analysis. So for all natural numbers m and n, we have d of mn is equal to d of m multiplied by n plus m multiplied by d of n. So this is the derivative, arithmetic derivative, and so now the logarithmic derivative is defined as the function LD, also from natural numbers, but now it's to rational numbers. So the values are not necessarily natural, and it is defined simply as the derivative, the arithmetic derivative over the number itself. So the arithmetic derivative of n divided by n. So now why is it called logarithmic? So let's examine what the product rule would look like for the logarithmic, for this function LD defined this way. So we simply see that when we write the arithmetic logarithmic derivative of the product m multiplied by n, so this is equal to d of m multiplied by n over m multiplied by n. Now the denominator, we leave it as it is. In the numerator we have basically this expression, so d of m multiplied by n plus m multiplied by d of n, right? Now we write it as as two fractions, d of m multiplied by n over m multiplied by n plus m multiplied by d of n over m n, right? So now we see that n cancel each other and m cancel each other. So in total this is equal to d of m over m plus d of n over n, right? So now we notice that this is exactly the logarithmic derivative for m. So this is equal to LD of m, and this is equal to LD of n, right? So in total we have logarithmic derivative of m plus logarithmic derivative of n. Yeah, so we see that this is equal to this. So let's, for convenience, let's rewrite this separately. So the logarithmic derivative of the product is equal to sum of logarithmic derivatives. yeah, so this is the formula, and it is actually similar to the property that we have for regular logarithms, right? So when the logarithm of the product xy with some base a, let's say, is equal to the sum, so logarithm of x plus the logarithm of y. So this is the formula for logarithms, and because of the similarity of this formula with this, it is called the logarithmic derivative, arithmetic logarithmic derivative. Yeah, so now let's examine the general formula for the logarithmic derivative. So it is simply derived from the formula for the full derivative. So for the full derivative, so in one of the previous videos I proved that if the number n is expressed as the product of prime numbers, right? So if it is the product of pi, where pi is prime, so pi are prime, all of them are prime, and there could be repetitions here, so like some of the prime numbers might occur more than once in this product. So this is the regular like expression of a number in terms of the product of the prime numbers. So then the derivative, the arithmetic derivative of this number n can be written as n multiplied by the sum of 1 over pi, sum by I, so for the same prime numbers. So, and this kind of it looks better, but sometimes like we also need to express n as like for different primes, basically for different prime numbers, and then when different prime numbers we need to account for the powers. So it's expressed as prime number pi raised to the power ni, certain power ni. So then the derivative is equal to n multiplied by the sum of ni over pi. This is basically the same formula, just written differently. Either we allow different prime numbers in the product, and then it is this, or we don't allow different prime numbers, but then we need to raise the prime number to certain powers. So, and in this case, like we see that there is this multiplier n. So when the logarithmic derivative is defined as divided by n, so it is very conveniently cancels. So basically the logarithmic derivative of n would be equal to, let's write like in detail, n multiplied by, okay, let's write fully. So it is equal to d of n over n, which is n multiplied by sum 1 over pi, sum by I, or n. Now n and n cancel each other, and we have simply the sum of prime numbers. Or if we choose this representation, it is also equal to the sum of well, we shouldn't, like from this representation, LT of n is equal to, so this representation was from this, and this representation is from this. So Ni over Pi. Yeah, so let's yeah, so it kind of looks like a beautiful formula. So let's consider an example. So for example, if n is equal to 12, so if n is equal to 12, it is easy to calculate the t of n, the derivative of, and well, we can calculate it from the product rule. It's simply, so t of 4 by 3, right? So it is d of 4 by 3 plus 4 d of 3. So this is equal to d of 2 by 2 plus 2 d of 2 by 3 plus 4 by 1, and this is equal to, because d of 3 is 1, because 3 is a prime number, right? And d of 2 is also 1, and this is also 1. So in total we have 2 plus 2, so this is 4 by 3 plus 4, so this is equal to 12 plus 4, this is equal to 16. So the arithmetic derivative of 12 is 16. Now the logarithmic derivative of 12, it's even easier to calculate it from the product rule. Like it would be LD of 4 by 3, right? So this is, or like we can write even now multiple. Oh, okay, let's write it this way. So it is LD of 4 plus LD of 3, and LD of 4 now is equal to LD of 2 plus 2, right? So 2 plus LD of 2 plus LD of 3, and for a prime number it is equal to, so the arithmetic derivative for a prime number is equal to 1. So when we divide it over the number itself, it would be 1 over the prime number. So 1 over 2 plus 1 over 2 plus 1 over 3. And this is, by the way, exactly the expression, like exactly this representation, because 2, 2, and 3, so 12 is equal to 2 multiplied by 2 multiplied by 3, right? So then it is equal to this, and yeah, and by the way, in this form it is even easier to, like this form, it is even easier to prove directly from the product rule. So from this product rule, it's like we don't even need to use the formula for d. So from the product rule, we simply write that. Okay, let's write it here. So from this, it follows that if we have an arbitrary number, so if we have like n1 multiplied by nk, so the LD of this product would be simply the sum. So LD of n1 plus and so on plus LD of nk. Well, we simply do it step by step. We first divide it as n1 and so on multiplied by nk minus 1 and the last one. So we apply the product rule to these two multipliers. We get the sum, and then we use the same for the nk minus 1 and so on. So it's easy to prove that this would be equal to this sum. And then when n is equal to this product, then we simply see that LD of n is equal to LD of the product of this prime numbers pi. By this formula it would be equal to the sum of LD of pi, and for a prime number, the logarithmic derivative is simply equal to 1 over pi. Well, because let's write here for if p is prime, then the logarithmic derivative of p is equal to d of p over p, and d of p is equal to 1. So this is equal to 1 over p. So this is equal to 1 over pi. And this is exactly the, like this formula. Yeah, so it is easy to prove even without using the formula for the full derivative. But so anyway, so for 12 we see that this is exactly what it is, and so for 12 is represented as this, so then the logarithmic derivative of 12 is equal to this sum, 1 over 2 plus 1 over 2 plus 1 over 3. This formula exactly, and this is equal to 4 over 3. So that's the arithmetic logarithmic derivative. So I think that's it for this video.